Anything on probability space, filtration, probability measures?
Good morning, sir.
Good morning, Siddesh. Go ahead.
Like last session, we had like two questions. The
Okay.
like you said that we will pertain this in this session. The
Okay.
relevance of biases in our natural probability measure.
Okay.
This is question one, and another like it was my personal question. Like, can you please revise or put more light on this concept? Like, we were on the standpoint. The you said that this is the point where the field data science takes a different turn and finance take different turn. Like
Yeah.
historical data needs data science and ML, and
Yeah.
quantitative finance was done way before we had data without data. So that
Yeah.
two questions I had.
Sure. Sure. So first is relevance of bias, right? I'll just point it out so that we don't miss it.
Yes,
Uh,
sir.
relevance of bias
Bias.
in P. Okay. And second is branching of of QF from ML, which is P versus Q. Okay. So we'll do that. Okay. But before we do that, we will kind of cover some context, right? Which is the leftover portion from our previous session. And so let us start in that context. Okay. So the context, the concepts which we are covering now are essentially number one, which is RadonNiko derivative, Rn derivative, which for which we have the statement of the form of like this. We will see what it means, and this is for discrete and this is for continuous random variable. Sorry. Okay, so we'll see the statements, and then we'll have our first assignment question based on this. Okay, so let us start with this. Now consider a simple coin toss, right? So a coin toss with omega is equal to heads and tails, right? And corresponding associated probabilities as 1/2/1/2. So it's a fair coin toss. Uh, Random variable x is defined as a function which maps omega to real numbers, right? In our case, the omega is heads, comma tails. So for sake of simplicity, we will map it to 1, comma 2, right? So what you can understand by this is if you flip a coin and you get a heads, you'll get 1 rupee. And if you get a tail, you'll get 2 rupees. Okay, something on those lines, right? So in our context, right, of our plain statistics, if I were to calculate expectation of x, correct, under probability measure P, okay, it is defined in discrete sense as sum of the probabilities of the outcomes, right, and multiplied by the outcomes, right, and I goes over the sample space, right? So we'll calculate it as 1/2 into 1 plus 1/2 into 2, right? So this turns out to be, 1/2 plus 1 is equal to 3/2, right? So this is our conventional statistics, right? Now let us define a probability measure Q, right? Probability measure Q on the same experiment, right? On the same experiment Q is defined as, let us say, let me put it as 1/3 and 2/3. Okay, so for the same stochastic, for the same probability experiment, if we have a different probability measure, okay, let us try to compute expectation under this probability measure. Okay, so expectation under Q for the same random variable X will be defined as, 1 by 3 into 1, correct, plus 2 by 3 into 2, correct. This will be 1 by 3 plus 4 by 3 is equal to 5 by 3. I hope everybody is with me. So far, so good. Now what we are trying to do is, we are trying to do, we are trying to compute this in a different way. Okay. So what we are going to do is, we are going to compute expectation under probability measure P of QIs on PIs, okay, multiplied by X. So there is a new random variable Z, okay, Z, okay, which I'm defining as, this is only for discrete case, Qi by Pi, okay, into X. So we are scaling our original random variable, okay, with respective probabilities for those respective outcomes, okay. So first, okay, so this will be defined as expectation of P, correct, and let us see what all we have, right. So we have Qi, right, so Qi is 1/3 and Pi is 1/2, right, into X. X is 1, correct, so which is omega I, right, the first observation, plus, so this is this, okay, and second outcome, okay, which is possible is, we have 2 by 3, which is this, and corresponding probability, right, which is again 1 by 2, okay, and then correspondingly X, corresponding X, so X in this case is 2, right. So we have expectation under probability measure P of, 1 by 3 divided by 1 by 2, right, so this gives us 2 by 3 into 1, okay, and here we have 4 by 3 into 2, right. I'll keep it as it is for now, correct. So I'll take expectation under probability measure P. So expectation is this first outcome, right, multiply by the probability P, correct, and then this outcome multiplied by this probability, okay. Let me use the epsilon pen. So this, okay, multiplied by this, and then this multiplied by this, okay. So what we end up with is, okay, 2 by 3 into 1, okay, into 1 by 2 plus 4 by 3 into 2 into 1 by 2, right. So we end up with 1 by 3 plus 4 by 3, right, is equal to 5 by 3, right. So this equates to this, right. Any questions so far? This is very important concept to understand, okay. We are now jumping from one probability measure to another probability measure, and this is a very central concept in quant finance, okay. So being able to move from one to the other is very important for us. Any questions so far? So let us come back to our first question for the assignment. Okay. I hope people will note it down. Okay, because I have not really written it well, but I hope you write it down. Okay. So this is your first question. So consider omega, okay, is equal to, so let us say you're playing a game, okay, and there are three possible outcomes to the game, and consequently you get three possible payoffs, which is $10, $5, and $1, or 10 rupees, 5 rupees, and 1 rupee. Okay, so already these are real numbers, so your random variable, you need not separately map it to anything else. Your omega itself becomes 10, 5, and 1. Okay. Now, what I say is that there is a probability measure P, okay, such that it assigns an equal probability to each of this outcome, okay, which is 1 by 3, 1 by 3, 1 by 3. Okay, so the question is, to prove that expectation under probability measure Q of X is equal to expectation under P, uh, Qi by Pi into X. Okay, where Q probability measure uh, is, I'll explain what Q probability measure defines here. Okay, just a small question. Okay, if you're betting on a certain outcome of an event, okay, and if a guy is ready to pay you, okay, 10 rupees for first outcome, 5 rupees for second outcome, and 1 rupee for third outcome. Okay, so what do you think is the likeliness of outcome of likeliness of the first outcome, or probability of first outcome, second outcome, and third outcome? Can someone tell me? The question is this, okay, the guy, you're betting with a guy, and the guy is ready to pay you 10 rupees, okay, if first outcome occurs, 5 rupees if second outcome occurs, and 1 rupee if third outcome occurs. Okay, so which is more likely event? Okay, 10, 5, or 1? You can unmute yourself and uh, say that
All
which
of
is,
these have,
sorry.
yeah, all of these have equal probability. So all of these have equal opportunity
No,
to.
no, no. What I'm saying is a guy is paying you different things for different payouts. Okay,
A one is more likely to happen as compared to a 5 and 10.
correct. That's right. Okay, because the guy who is paying you out is not a fool, right? He'll pay you proportionate to, what is less likely to happen. Higher amount will be paid for that, and wherever he's paying more amount, wherever he's paying more amount, that is less likely to happen. Wherever he's paying less amount, that is, more likely to happen, which is why he's paying you less for that. Okay, now keep that concept in mind. Okay, and that is your probability measure Q. Okay, so I want you to first find what that probability measure Q is. It is supposed to be a valid probability measure. Okay, and then under that probability measure, you have to prove that expectation of this random variable X, okay, where these are the outcomes, okay, is equal to expectation under your original probability measure into Q by P, okay, into X. Okay, I hope everybody got this question right. I know I have not explicitly written it down, but yeah, this is the question. Is there any confusion? Is there anything unclear about this question?
So should we prove that Q is actually a valid probability measure
No, no,
using?
no. First, you need to find a Q such that Q is a valid probability measure. Okay,
Okay.
as per the definition which I have mentioned. After that, this is your actual problem, assignment problem, right? This is not the problem. This is the sub part of the problem.
Okay. Got it.
Okay. Yeah, there was an extended part to this question, but if someone finds, so I have structured assignments slightly differently, okay, because everybody's learning pace is not same, right? If someone finds that the question which I have posted is very trivial, okay, and it's too simple to solve, okay, and you solve it in maybe a couple of minutes or 2-3 minutes, okay, then an extended problem for you, okay, is to to prove it numerically. So first you prove it numerically, so you have your answers right here. Then the next step is to write a Python code to cross check your results, okay. And let me tell you what that code is supposed to be, okay, or rather let me tell you what that code is not supposed to be, okay. The code is not supposed to be, okay, for example, you have written out p, okay, as a list which is 1 by 3 1 by 3 1 by 3, okay, and then you multiply by x, okay, which is 10 5 1 by 3, okay, and take cumulative sum of it, okay, okay, and call that as probability or call that as expectation under probability measure p, okay. I'm not expecting this, okay. What I'm expecting is, okay, okay, the algorithm, okay, which on the lines of which I'm expecting, and this is first assignment, so I'll tell the algorithm, but going forward I'll even want you to think and come up with the algorithm yourself, okay. Any and every Python code which we are going to write is going to start from the first principles, okay. We are not going to use any custom Python libraries or any analytical solutions which we have derived as a form of our academic exercise, right? So we have derived here analytically what is going to happen and all. I don't want you to use that, okay. What I want you to do is perform that experiment using the computer, okay, and generate the outcomes, okay, and see that as as number of your trials tends to infinity, as n tends to infinity, whatever answer you get numerically via Python, okay, that approaches as to what you got as per your analytical answer, okay. By that what I mean is, again, like I said, I'll explain it in a little detail here, okay. So let us go back to our this, okay. So this is a little easy for me to write. So the Python code will look roughly like this, okay. So you will write, okay, so you'll write something like this. Let me hide this so that we can come back to the black, okay. So you'll write a function, def random number generator, okay, such that the outcome of this, okay, is okay, is going to be a number, okay, between 0 to 1. It can be yeah, it can be yeah, it will be a number between 0 to 1, okay. So you have a random number generator, okay. Then you will use this random number generator to split your outcomes, okay, in probabilities, let us say 1 by 3, right? So what you will say is, then you will define random variable generator, okay, okay, as a function which uses random numbers, okay. So let us say here you generated certain random number, okay. So Rn, let us take 3 examples. First Rn was 0.25, then Rn became zero point 0.6, and then Rn became 0.8, okay. Then you will write here the cases, right? If, okay, Rn is less than 0.33, okay, then assign the random variable x as value of 10. Similarly, you will write if Rn lies between 0.33 to 0.67, x is equal to 5. And if it is greater than 0.67, then your x is equal to 1, right? And then you will perform this experiment again and again. So you will get stream of x, right? So you will get a list. So then you'll perform the experiment. Okay. So experiment as a function, right? What it does is, if I pass number of trials as input, okay, what it does is it will, so if I say n is set to 100, okay, then it will generate this random number 100 times. Okay, so you'll get xn is equal to x1, x2, so on up to x100. Okay, so you got this. Okay, and you take expectation. Okay, expectation statistically is defined as taking the average. Okay, so you'll define expectation xn, okay, is equal to x1 plus so on up to x100 divided by 100. Okay, and then you will keep increasing this, right? So 100 you will make it to 200, then 500, then 1000. Okay, then your this expectation of xn, okay, will converge to this. I mean, it will converge to this expectation under probability measure q of x. Okay, you have to cross check whether this converges to this. This is your first step, right? The second step will be in the code will be, okay, to redefine, okay, or let me call it as transformed x. Okay, write a function called as transformed x. What it will do is it will define x underscore new is equal to x into qi divided by pi, right? So you get a new x, right? So, and from this x new you perform the experiment again. Okay, repeat the same steps. Okay, and then get the average again. Okay, so this will be expectation under q of x, right? So expectation under q of x, okay, is equal to expectation under p of this transformed x, okay, is equal. Okay, this is what you need to check. P of qi divided by pi times of x. Okay, the only custom library which you can use here, okay, which are allowed to use here, is there is a maybe Python library to generate uniform random numbers. Okay, only this custom library you are allowed to use. Apart from that, you're supposed to use for loops and all of that. And at the most for this list, so this you can keep it as list. Okay, this you can keep it as list, or you can make a data frame out of it. Okay, the data frame will look like this. The row will be like trial 1. Okay, and column will be what you get here, right? So you get 10, 5. You get this experiment again and again, and you redo this experiment, trial 2, trial 3, right? And then you take the average of first, okay, and then average of second, and then average of all of this if required. Okay, so there are many ways to do it, but this is a high level summary of if someone wants to reproduce this experiment, right, using a Python code, then this is how you are supposed to do it. Any questions so far?
Yes. So the code should be abstract instead of like fixed probability values of 10, 5, 1, right? But the sample space should remain only 3 values, 10, 5, and 1, only 3 possible outcomes.
No, so sample space will always be 10, 10, 5, 1, right?
Okay.
Only the probabilities change. Okay. First, the probability can either be 1 by 3, 1 by 3, 1 by 3. Okay. If it is same, then you are using this condition. Correct. Then you are using this condition to generate the experiment. Okay. If it is q, if it is not this, if it is q probability measure, right? If it is Q probability measure, then you will redefine that if Rn is less than Rn1, okay, whatever you will get from solving it, right? Then you assign x is equal to 10 and so on and so forth. Only these changes, these are intervals changes. Let us say for the sake of argument, right? If your Q is okay, so this is supposed to have so this is supposed to have higher probability, and this is supposed to have lower probability, right? So let us say this is the least probability, right? 0.2. This is higher, 0.3, and let us say this is even higher, 0.5, right? Then your just these intervals change. 0 to 0.2, you call that as 10, 0 to 0.2, whatever, right? So, and then correspondingly, you get your x's. Okay.
Right, got it.
Yeah. So this is our first question, right? So like I said, I have split the question into two parts. If someone is feeling, they are struggling with basics themselves, right? Even if they are able to do it numerically, right, it is well and good, right? You can stop at that point in time, and we can move to the next topic. If you feel that it is too simple a question, right, and then you want something to build on that, right, then you can write a Python code. So explaining something to a computer is a very so what I can say is computer is the dumbest person that you can explain something to. Okay, if computer understands it and matches with what you're observing, then most likely you have written a very good and a correct code. Okay, any questions so far? Okay. No questions? Then we'll move to our next topic. The next topic is this. Okay, so we are going to define stochastic process. Then we are going to define random walks and some results we are going to see for that random walk. Okay, so I hope we are ready to go, right? Because this topic in itself will take us at least I don't know, half an hour to 1 hour, right? And then we'll have a break post that, right? So I hope everybody's okay with it. So let us go with definition of a stochastic process, right? So far so good. We have not formally defined a stochastic process, but let's start with it. Okay, so stochastic process is defined as time indexed random variables. Right. So when you're performing an experiment and whatever outcomes you keep getting out of it, okay, so here is your omega, which is collection of omega i's. Okay, apart from that, when you start associating time for it, okay, which is omega I at time t, okay, then the collection of these random variables is called as a stochastic process. We'll keep coin toss as a very central experiment, which we'll be using again and again for any concept which we see. Okay, so for concept of stochastic process, we'll see the coin toss. Then for process of random walk, we'll see coin toss. For Markov process, martingale will see coin toss. For binomial pricing later also, okay, we'll see coin toss. So we'll keep coin toss as a very central experiment so that our concepts are relatable. Okay, we don't introduce new experiments each time and confuse ourselves. So that is why I'll keep the coin toss as a very central concept to it. Okay, so so we have coin tosses, right? So we have a coin toss, okay, which has omega of heads and tails, correct? Now let me associate a random variable x to it, okay, such that omega maps to +1, okay, or -1, okay, and a probability measure p, okay, such that it is 1/2, 1/2, right? So let us start from here, okay. Let me just point it out, okay. So you start from here, okay. So what happens is at time t is equal to 0, you begin the experiment. So at time t is equal to 0, you have begun the experiment. Then with probability 1/2, okay, you might end up at being +1, or at with probability 1/2, you might end up at being -1. And if we go at, so this is time is equal to 1. Okay. Okay. So and let me clean this up also. Right. So we can be at -1. Then from here, right, given that you're at +1, right, with probability half, you can go to 0. And from here also, with probability half, you can go to 0. Similarly, with probability half, so here we can go to 2, here we can go to, -2, right? And we continue it for only one more step. With probability half, you can go to 3, right? Or with probability half, you can go to 1. Then with probability half, you can go to 1. With probability half, you can go to -1. With probability half, you go to -1. And with probability half, you go to -3, right? So the stochastic process ST, okay, which is sum of xi's from I equal to 1 to t, okay, where xi is defined like this, okay, is called as a random walk. Okay. Any questions so far? Right. So can can someone tell me what is omega of this random variable st?
-3 to 3.
Yeah, in this case, since we are stopping the experiment here, okay, is 3 1 minus 1 minus 3. Okay, so and if we are okay, so let us write it out. Okay, so what happens is, let us make a table out of it. Okay, at t equal to 0, let us see omegas. Okay, so at t equal to zeros, sorry, at t and omega. So at t equal to 0, right, you have omega equal to 5. At t equal to 1, you have the possible outcomes as +1 minus 1. At t is equal to 2, right, you can have the outcomes as 2, 0, minus 2. At t is equal to 3, you can have outcomes as 3, 1, minus 1, minus 3. Okay, can you find a pattern here?
Sir, the difference between each two variable is 2.
Sorry.
The difference between each element in the sample space is 2.
Okay, so that is one observation. Okay, but
Will
for example,
span from 2 power t minus 1 to negative of that value in steps of 2.
2 power t minus 1. Okay,
To minus of 2 power t minus 1.
2 minus of 2 power t minus 1. Okay, let us check this. Okay, but there is an issue with this. Okay, but let us see. Okay, let us put t equal to 0. It's trivial. Okay, let us put t equal to 1. Okay, then what happens? T equal to 1, this is 2 to the power 0, right? And this becomes minus 2 to the power 0. So this spans from 1 to minus 1. Okay, which is all right. Now, if I say 2 to the power, t is equal to 2. Okay, then what happens? It spans from 2 to minus 2. Okay, but you don't know what is there between that. Correct? Plus, if I write t is equal to 3, right? Then you're supposed to span from 4, correct, to minus 4, which is not right. Correct?
Sir, if the value of t is taken as n, then the size of psi will be equal to 2 की power n minus 1 plus 1.
Yeah, but that's not my question. My question is, if I have to write the outcome, okay, omega at t is equal to 5, how do I write it?
So essentially for that we can do is we can start from -5 and then keep on adding 2 till we reach till 5.
Okay, so you are starting from -5. Okay.
Yeah.
Okay, and then you'll keep adding 2 to it.
Yes.
Okay, so that you reach up to 5. Okay, that's a good observation. So let me redo it, or rather restate it, the same thing in a different way. Okay, so let us say I'm asking you, after n coin tosses, what all positions you can be in. Correct? So after n coin tosses, what happens? Okay, sometimes you would have received heads, right? And sometimes you would have received tails. Correct? So let us say totally you have done tosses 5 times. Correct? Now, if I tell you, okay, that you have heads, or rather, +1 or whatever, okay, at k times, okay, how many times have you had tails? N minus k times. Correct? So what is your position going to be? If x is a random variable which tells your position, what is your position going to be? K times +1, okay, plus n minus k times -1. I hope everybody is following this. So my question is, how do you reach -1 here? You're supposed to reach -1, okay, at t is equal to 2. Okay, what are the ways to reach it? You have t equal to 0, 1, 2, and 3. Sorry, this is t is equal to 3. My bad. This is t is equal to 3. Okay, at t is equal to 3, what are the ways to reach -1?
From 3 steps, you pick any two and you
So
take the step towards -1, and in the remaining steps you take +1.
yes, that is right. So if you have 3 steps, okay, total 3 steps, okay, then out of which 2 have to be negative, right? And the order does not matter. And 1 has to be positive, okay? And let us see that. Okay, so here you have taken, so we'll keep a track of positive and negative steps, okay, positive and negative. Let us take this path, okay, it went up, okay, so it took first positive, okay, then it went down, right, so it took one negative, it took another down, so it took another negative, correct? So here we had k is equal to 1 and n minus k is equal to 2, okay. Now what is the other path it can take to reach at -1? Okay, it can start with first down, okay, and then up, okay, and then down, correct? So it can start with going up, sorry, going down, okay, then going up, okay, and then going down. This still ends up at 2 downs and 1 ups, okay. Is there any other way to reach -1? There is another way, right? So you can go down, then you can go down, and then you can go up, right? So you can go down first, and then up, okay. It still adds up to this, okay. So total there are 3 ways to reach -1, correct? And the generic equation, right, which tells you what will be the position of, or what can all be the positions of x, okay. If you have taken n steps, out of which k are positive, right? So as you can understand, k can range from 0 to n, right? So this is a way to generically define your sample space. This is equal to k into +1 plus n minus k into -1, right? For all k belonging to 0 to n. Okay, this will definitely cover your full sample space at time after n coin tosses. Any questions so far? No questions?
No, let's continue.
So now the question is, what is the probability of reaching X? Okay. Probability of reaching X given n coin tosses. Okay. Now let us try to do it for -1 itself. Okay. And then generalize. Okay. What is probability of reaching at -1? Okay. So there are total three ways. Three ways to reach -1. Correct? And for each of the way, okay, so uh, if you are doing 3 coin tosses, okay, what we have decided is 2 have to be tails and 1 has to be heads, right? So you can so these 2 tails can be any 2 tails, okay, and this head can be any heads, right? So you can have, all you're supposed to have is 2 tails, okay, so 1 heads and 2 tails, or you can have, you know, THT, sorry, okay, or you can have TTH, right? So any of these three will, I mean, so your event is this, so you need to add up this probability plus this and so on and so forth, okay. So this is, I think, a very standard result, right? This is given by, can someone tell me how is this given by? I think this should be a sufficient enough clue, right?
It will be 3C2 into 1 by 2 cube.
Yes, it will be 3C2 into 1 by 2 cube. Okay, that's right. But let us write it a little more generically, right? It will be 3C2 into 1 by 2 square into 1 by 2. Sorry. This reminds someone of something.
Binomial.
Yeah. So this follows a binomial distribution. Okay. What are the parameters of binomial distribution?
Total number of tosses, that is n,
Okay.
and the probability of either
Correct.
getting head or tail.
So here total number of tosses are here again the same, total number of tosses. Okay. And here in this is a symmetric random walk, right? So we I mean not symmetric because of that, but this is a fair coin toss, right? Because of which you have probabilities associated as 1 by 2 1 by 2. Okay. If instead I had associated a probability of P 1 minus P, okay, then you would have required a more formal thing, right? So okay, so you require NCK, you know, Q to the power K and P to the power N minus K.
I have one doubt here.
Yeah.
So this is not exactly binomial, right? Because we need another constraint. If we are going to say that we are going to get the score of x,
What is that?
like here in the n choose k, q raised to the power k and p raised to the power n minus k. So that gives us the like number of times I'll get the event k and the event k number of times, and my rest of the times I'll get whatever event is associated with probability p, right? But
Right.
for score to be x, so our +1 and -1 cancels each other. So like the absolute difference
So
between
your x itself is defined here. Okay. X itself is defined here. What values it can take and it cannot take is defined here. I think what you mean to say is if t is equal to 3, right? What you're saying is you cannot get 2. That's what you're saying, right?
right.
So that itself gets defined here. Correct?
Okay.
I am saying that x cannot, I mean, what values it can take and it cannot take, it is predefined here. I'm saying that itself depends upon number of coin tosses. Okay. And within that, how many times you have got heads and how many times you have got tails.
Okay.
That is why this is a valid probability in that sense. Okay. So you are not missing out any elements, or I mean, there are no elements for which no probability is associated, or there is no thing that probability is associated, but that element does not exist. Okay.
Right, like the formula of x that translates to 2k minus n, that won't be able to take certain values, either even or
Yes.
odd, something like that. Right.
Yes. So this, right, you put it rightly. So you have k plus sorry, n plus minus n plus k, right? So x is equal to 2k minus n. Okay, so first you need to know what is your x, then you can associate a probability with that. Okay.
Right. Got it.
Now, okay. Now, what is expectation of a random walk, right? Now comes the question, right? Expectation of ST. Okay. Can someone tell me what is expectation of ST? So expectation is defined as probabilities multiplied by outcomes, correct? So if so, in this case, in our example, right? Let us try to work it out numerically one by one, okay, and then see what happens. Let us take t is equal to 1 only. Okay, so what is expectation of S1? S1. Okay, that is equal to 1 by 2. Okay, into plus 1 plus 1 by 2 into minus 1. This is equal to 0, right? Now what is expectation of S2? Okay, expectation of S2 is equal to, okay, 1 by 4 into 2 plus, can someone tell me what is probability of 0?
1 by 2.
Right, 1 by 2 plus 1 by 4 into minus 2. Okay, this turns out to be 0. Okay, and so on and so forth. So expectation of Sn is equal to 0. Can you tell me this is true under what constraints? for all,
equally likely.
that is half answer. Okay, that is half answer. Yes, it is true in equally likely context. I mean, given that it is equally likely, that is why it is 0. Okay, but that is only half part of the constraint. Can someone tell me what is the other half of it?
It's
Because
a
of the
type of
A,
zero-sum game.
Again, that's not fully complete answer. That is correct. Okay, but not a fully complete answer. Yeah, I mean, yes, correct in that sense, that because you have only two outcomes, right? And since this is zero sum, so both of them are equal and opposite in magnitude. Okay, that is why 1/2 helps. Okay, so let us write it generically. Okay, so let us write it for a generic thing. Okay, and then see what happens. Then you have here P, correct? I say here this is plus L. Okay, this is 1 minus P. Then you have minus M. Then what happens? Then your expectation is equal to P into L, right? Plus 1 minus P into M. Okay, so your expectation is not 0. Okay, I hope everybody understand that this is a non-trivial result. Okay, so if someone asks you what is the expectation of a random walk, the answer is not a blatant 0 always. It depends. If it's a symmetric fair random walk, then yes. If not, then it depends. Okay, so either so there is a relation, right? Now let us say we want this to be explicitly 0, correct? So we want P into L plus 1 minus P into M to be 0. Then what is the condition for that? P into L is equal to M into P minus 1, right? Therefore P by M, L by M is equal to P by 1 minus P. Okay, so if you have been given L and M, okay, then you can solve for P, right? Let us do that. P into L is equal to, or rather we already had it here, right? P into L plus M minus M into P is equal to 0, right? So let us take P common, right? Then you have L minus M is equal to minus M, right? So P is equal to minus N upon L minus M. So can I say that for given set of outcomes, okay, if the outcome is plus 1 minus 1, okay, there is P, okay. If I change these outcomes, okay, to L and minus M and all of that, there exists a P a unique P for all L's and M's such that expectation of Sn is equal to 0. Is this statement correct? Is this statement right? This is extremely important statement. Okay. For example, here our equation is equation in one variable slash it's a linear equation, right? If this equation were of the form p square a plus pb plus c is equal to 0, this would have meant that p has two solutions or can have two solutions, correct? Now given that p has only single solution, it means that there exists a unique probability measure p under which, okay, expected value of random walk is 0. Where does random walk begin with? Random walk starts with 0, correct? Here I did not explicitly mention it, but it starts with 0, correct? So this is a very important condition. Okay, we'll go through this later and all again and again. Okay, but this ensures no arbitrage. Okay, this is also called as fundamental theorem of asset pricing. Okay, and this gives rise to the fact that we can price derivatives in a unique way and only one single way, or one single derivative instrument is not going to have multiple prices because you're not going to have multiple p's for which a certain condition is satisfied. We'll see later what that condition is. For random walk, that condition is this: expected random walk is equal to 0. But generically, we'll see what that condition is for derivatives. Okay. So any questions so far? We have technically covered a lot of ground. Okay, you may or may not realize it. Okay, RadonNiko derivative is not, I mean, it is taught rigorously, but generally it is taught with a lot of mathematical symbols and a lot of things, right? Random walk, I don't know, right? You must have seen that. You will see how it evolves, your p's, q's, and all of that, right? But then there is a very strong statement which is being made here. Okay, and this forms a cornerstone of existence of a q probability measure for pricing of derivatives. Okay, so currently we are building very strong foundations on the top of which we can build pricing of derivatives. Okay, any questions so far?
Yeah, just one question. So while pricing the assets, do we assume that they follow random walk?
Yes,
Okay.
exactly. We are going to see two ways of pricing. We are going to see two ways of pricing derivatives. I mean, there are many ways, but first is going to be discrete, which is going to have binomial model, which is very similar to what we are seeing now. And the second is continuous, which goes into Black-Scholes and a lot of other things. Okay, so we are, establishing a base for everything. Okay, in discrete sense from here. If this holds in discrete sense, there are equivalent continuous sense where it is supposed to hold, and that is why we can go into direction of Black-Scholes and all of that. Okay, any questions so far? If not, we'll proceed to one final concept which is left here. Once we cover this, we'll have our second assignment question, and then we'll take a short break of 5 minutes. Okay. The question is this. Okay, so there is, so after you have traversed some time, okay, in the random walk, after you have spent some time, let me rub a few things. So it has taken me, referring quite a few references. Okay, you will not find everything structured in exactly same way anywhere in any book. Okay, you'll find it structured differently in different places. Sometimes they start very generically, directly with only generalized version of it, and then since we don't follow step by step, okay, we might miss. And sometimes they do it very basic or very elementary. Okay, so you don't see the generalized version of it, or the large scale application of it, which is why, having such course, any course, okay, you can learn it from anyone, but having a structured course being delivered by someone, right, it helps in this sense. Okay, I myself find it difficult to, for that is why so far so good I have not yet recommended any good source for you, that okay, read this and you will find these concepts in the same sequence everywhere. Okay, which is why I have not recommended it yet. Okay, now let us go one step further from here. Okay, we are at 3 and 1 by 2 to 4 or 1 by 2 to 2. From 1 with 1 by 2 to 2, with 1 by 2 you can go to 0, with 1 by 2, with 1 by 2 you can go to -2, right? And then with 1 by 2 you can go here, and then with 1 by 2 you can go to -4, right? So we already know that if you are supposed to reach at a point, how do we calculate its probability? Correct. So we have so far reached here, right? Let us calculate probability of reaching here. Okay, so what is the probability of reaching at x is equal to 0 given, n is 1, 2, 3 and 4. Okay, n is equal to 4. Okay, now can someone tell me this probability? Okay, as you must have seen, we cannot directly find these probabilities, right? Before finding this probability, we need to find how many times we have to go to the right and how many times we have to go to the left. Okay, so 0 is essentially at the middle of it. So if totally you are going to toss it 4 times, you should have gone 2 times to the right and 2 times to the left, right? So you should have done like this, right? And then 1 by 2 to the power of 2 and 1 by 2 to the power of 2. Okay. At the same time, okay, we know what is the probability of reaching at x is equal to -1, right? Given that we have 3 coin tosses. Okay, so probability of reaching at x is equal to -1 given that n is equal to 3. Okay, so for this you need 2 downs, right, and 1 ups, right? So but this will be 3c2, right, and 1 by 2 to the power 1 and 1 by 2 to the power 2, right? Similarly, if we have to so we have to reach here, correct? So what are ways to reach it? So from t is equal to 3, what are ways to reach at, so given that you are at x3, right? You are calculating probability of reaching at x4 is equal to 0. Okay. So what can happen, right? There are only two ways to reach from x3 to 0, right? Which is first reach at x equal to -1 and then 0, or reach at x equal to 1, right? And then 0. So I will say that probability of reaching at x equal to 4 given x equal to 3 can be written as probability of reaching x equal to 4 equal to 0 given that x3 was at -1, right? And probability of reaching x4 is equal to 0 given that x3 was at 1. Okay, but if you are at -1, right, you need to go up. Okay, not all -1 paths go to 0, some of them go to -2 as well. That is why you need to scale this up with its probability of reaching 0, and this with probability of from x equal to x3 equal to 1. Okay, from there reaching probability equal to 0, right? So, or rather this is now not required. Okay, so you just require these. You're already reaching. Okay, so you just require these. Probability of reaching at x equal to -1 and probability of at x equal to reaching at from 1 to 4 and from -1 to 4 equal to 0, right? So if you calculate these probabilities, right, which we have calculated here, right? So probability at reaching x equal to 1 given n is equal to 3, okay, is equal to 3c2, right, into 1 by 2 square into 1 by 2. Okay, so if you substitute all these things in respective places, right? So in this place, okay, place Yeah, sorry for the inconvenience. We can take a short 10 minutes break and let us start at 10:40. Yeah, so I'm back. While we wait for others to join, right, and start at 10:40. Is there any question which anybody else has for now? Hello. Hello.
So in random walks, when we saw the mathematical derivation of that there has to be this unique pricing, right?
Yeah.
Of the where you can start at 0 and reach at 0.
Yeah.
So the mathematical derivation of it seems so simple that right now it seems quite difficult to uh, see the impact of it right now. So are we going to discuss about this further
Yes.
in
Yes. Yes.
later classes?
We will. We will. So this was just an introduction that it is unique. We are going to see what are implications if it is not unique and all of those things. So that is very central to our whole QF. Plus we'll see it in binomial pricing. We'll see it in Black-Scholes model. So many times the same thing will keep coming up. But what happens is when we reach at that point, at that concept, right? And when I say that this holds because there is only a unique probability measure, right? Then if we are not sure of the basics, the first question is then what is a probability measure? Are there multiple probability measures to the same stochastic process? Why? What happens if it is? I mean, why is it? I mean, why is it only a unique? Right? Why can't there be multiple? So all these questions start popping up at that point in time, not now, really. Okay. So for that, we need to be sure of our basics. So if our basics are not clear at that point in time, we'll get a lot of questions. And the answer to that question, again, we have to keep going back and discuss same things again and again, right? That is why I have been stressing that it's better if you follow these things step by step, right? Most likely you will ask, where is random walk used in derivative pricing directly, right? Directly it's not used, okay? But the concepts and establishments of foundations build on that so that we reach to that stage. Any other question from anyone? So all these concepts, right? Brownian motion and all, these are not applicable only to quant finance. These are used in modeling at multiple places. That is why if you look at a literature which talks about Brownian motion or random walk only, you will see that it is treated very mathematically and not necessarily through finance and unique probability measure and all of that. Okay. That is why it's difficult to find one single good source which talks everything end to end. Okay. Although I'll recommend certain sources where you can go through these things. So I think the point where we had stopped earlier, right, was finding the probability that at after n coin tosses, it is at, so this is essentially what we are trying to establish. Okay, so after n coin tosses, okay, when it is going at n plus 1 coin toss, and it is supposed to go at x, right? And to begin with, it is at y after n coin tosses, and after n plus 1, it is supposed to go at x. Is there a relation between these two probabilities, right? And we are trying to establish that yes, there is a relation, and this is that relation, right? So the relation is, if you were to multiply the probability of being at x is equal to -1, so there is a probability associated with it, and there is a probability associated at being at x equal to 1. And if you want to find what is probability of being at x equal to 0, okay, that probability is given by this probability at being at x equal to -1 into 1 by 2 plus being at 1 into 1 by 2, that directly should give you this probability. Okay, so finding probability of here can be done to through ways. Either you can start from here, okay, and count how many zeros and ones you have, okay, and then take 4c2 and all of that. But if you already know what is the probability here, okay, at t equal to 3, you can directly find what is probability at t equal to 4. Through all the ways it can go from t equal to 3 to t equal to 4 for that particular case. If you find all the ways and if you count it up and multiply with the probabilities, then you get this probability. Okay, this is again, this might look like very trivial and very elementary, right? Like, what's the big deal? Okay, this is the case, but this is a very central equation in again quant finance. Okay, and more popularly, if you read up some literature, it will be called as Fokker-Planck equation. Okay, so it tells you how you are connected to going forward in time and all of that. Okay, so this is the continuous version and all of that. Right? So if you are standing at a certain Yeah, sorry for the technical glitch. Had an issue with my net. So I hope everybody has so far so good followed everything. In case there are any questions, people can ask now, raise now. You can hear me, right? Hello?
Yes, sir, we can hear you.
Okay, so let's continue, right? So the assignment number 2 for the day is, check this relation. Okay, check this relation. I hope everybody has understood what this relation is, right? And I also gave a numerical example, right? So let me write it down. So the assignment number 2 is verify, for a random walk, right? Probability of X being at n plus 1 is given as sum over all the paths of marginal probability, right? That is this, right? Into probability of being at y, that is this. Okay, so these probabilities multiplied by these probabilities, okay, is equal to 1. Like I said earlier, we are going to perform a probability experiment. Just like we did for assignment 1, we are not going to what should I say? We are not going to multiply the numbers and show that they match. Okay, they will obviously match, but we are going to perform an experiment, right? So you are going to do trial 1, okay, and find what is probability at this. Then you can do multiple iterations, okay, and come here, okay, and then see what is probability of this, and then this, okay, and then verify this relation. Okay, I hope the question is clear to everyone. Are there any doubts with the assignment question?
So you have to verify it without using examples, like in abstract manner,
Yes.
right?
No, yeah, you can use numerical examples. Okay, what, for example, what can happen is, okay, if so, as you have seen, right, numerically, I mean method, I mean we have to do it manually. It is because we took t equal to 3 and t equal to 4, it is easy, right? We just have 2 paths. But if you are supposed to start from, t equal to 1, okay, from 0, right, then possibly there are more paths, okay, which reach to 0, okay, or from here or from here, right? There are more paths. So if a user inputs these 3 things, okay, he says that total my number of coin tosses are going to be 10, okay, then prove to me that if I start from okay, at x is equal to 5, okay, at t is equal to 5, okay, then my probability of reaching, okay, at x is equal to 8, okay, given that I start from here, okay, follows this rule, okay. So this is what your code output should be. So on left hand side you should have this, okay. On Android right hand side you should have this, and then you can show that these two match. You can verify it, okay. If you want to cross check it, you can cross check it for the example which we have solved, but your answer has to be more generic. Because if I were to solve this, if I were to ask you to solve this for n is equal to 271, right, where x starts from x equal to 3 at time t equal to 2, correct, and probability to go to, you know, at rather, let us use the correct symbols, okay, from y is equal to 3 at t is equal to, you know, 3, okay, to, you know, x is equal to 251 at n, okay. So what is this probability and how it is connected to the intermediate probabilities, or even to this probability, right? For example, if it is at 97, you can't do this manually, right? I mean, it will take way too long to do it, which is where the value add of code comes in. Any questions so far?
No.
I hope I have made the outcome clear, that this is what I expect as an output. So, okay, I'll keep this as an example because if you need to refer to. Okay, so let us move on to the next topic. Okay, the next topic which we have is, you know, again, analysis of what we can say, analysis of a random walk, but through a more structured example of gambler's ruin. How many of you have heard of this problem, gambler's ruin problem? Okay. Wait, I had prepared a whiteboard for it. Yeah. So this is our gambler's ruin problem. Let me set the context first, and then we can go into detailing about how do we solve it through Markov chain. I mean, random walks and all. Okay. So okay. So let me start with the problem statement. Okay. So you are a gambler. Okay. And you start with initial wealth. Okay, so your initial wealth is 10 rupees. Okay, the question is, if you so you you place bets. Okay, the bets are such that with probability 1/2, okay, you'll get +1 rupee, and with probability 1/2 you get -1 rupee. Okay, so 10, so just after first bet, right, you can end up with 11 with probability 1/2, or with 9 with probability 1/2. Okay, so if you play this game, okay, you're considered as a winner. Okay, if you accumulate wealth, okay, terminal wealth of 100. Okay, and you are considered ruined. Okay, if terminal wealth is 0. Okay, so the question is, what is the probability that you start with certain initial wealth, okay, that you win this game, okay, or, and of course the probability of getting ruined is 1 minus that, right? So let us start with analyzing this problem, okay. So let us say you have an initial wealth I, okay, such that I is between 0 and n, where n is equal to 100, right? So what happens is either at this point in time, right, you can, at this point, either you can go to I plus 1, right, I plus 1, or you can go to I minus 1, right? So you're going at I plus 1 with probability P, okay, equal to 1 by 2, and Q equal to I minus 1, 1 by 2, okay. But let us do it a little more generically, that is for P and Q, okay. Now let us see what happens, okay. Just now, okay, just 5 minutes back, we did one derivation, right, where we had seen that if you are at a certain point, right, then from that point to just next point, if you have to go, those probabilities are connected, okay. So let us say your probability of winning at point I is Pi, okay. So can someone tell me how it is connected, okay, to Pi plus 1, okay, and Pi minus 1?
So Pi plus 1 should be probability of winning into Pi plus probability of losing into Pi minus 1.
So
No,
probability of
sorry.
I, yeah,
Probability of I,
yeah,
Pi should be
okay,
equals to probability of winning, let's call it W into Pi plus 1 plus losing, let's call it L. So L into
okay,
Pi minus 1.
good. But what we'll do is we'll continue with our notations, right? So Pi
Right.
will be equal to P into Pi plus 1, right, plus Q into Pi minus 1, right? I hope this is okay with everyone. So this is a recursive equation, plus Q times, I'm just writing it better, okay. Now what I can do is this, so here there is nothing, right? So here I can write it as 1, right? So then I can split it up, saying that, this is P into Pi plus Q into Pi is equal to P into Pi plus 1 plus Q into Pi minus 1. Everybody with me so far? Then if I rearrange the terms, right, that if I bring this to here, right, and this to here, right, so you have Q into Pi minus Pi minus 1 is equal to P into Pi plus 1 minus Pi, right? So if I rewrite it, right, so Pi plus 1 minus Pi will be equal to Q by P times Pi minus Pi minus 1. Now let us look at some numbers, okay. Let us put I is equal to 1, okay. Then what happens? Then P2 minus P1 is equal to Q by P into P1 minus P0. Okay. Now can someone tell me what is P0? What is value of P0?
The initial amount that he has.
Yeah, so so you need to understand the notations, right? What does PI mean? PI means probability of winning. Okay, if he is at I or he has wealth of I, correct? So what does P naught mean? P naught means probability of winning, right? If he has zero wealth, correct? But we already have defined a zero wealth event as a ruined event, correct? So he's already ruined if he has reached zero. Okay, so therefore probability of winning after you have been ruined is zero, correct? So P2 minus P1 is equal to Q by P into P1. Let this be equation 1. Now let us keep iterating. Okay, let us keep I is equal to 2, right? So I is equal to 2 gives us what? In here, if you put I is equal to 2, right, then we get P3 minus P2 is equal to Q by P times, you have, P2 minus P1. What is P2 minus P1? So P3 minus P2 is equal to Q by P times, Q by P times P1. Okay, from 1. So P3 minus P2 is equal to Q square by P square times P1, right? So what can I write generically? Pi plus 1 minus Pi is equal to Q by P to the power I times P1. Right? So okay, so again there is some clever trick, right? This is one result. Okay, so equation number 2. Now let us start with something new. Okay, what is Pi plus 1 minus P1? Okay, can this be written as summation of Pi plus 1 minus Pi, sorry, Pk plus 1 minus Pi over all this sum? Okay, where Pk, where k equal to 1 to I. I hope you can follow this, right? Because what will happen is if we expand it out, right? So what I'm saying is P10 minus P1. Okay, what I can write it as P10 minus P9, right? Plus P9 minus P8 and so on, right? So these get cancelled out and we are left with P10 minus P1. Okay, so this thing I can write it as sum of these things. correct? But these things are individually these things, correct? So this is equal to sum of q by p to the power k times p1, where k equal to 1 to I. Okay. Now what I can do is keep I plus 1 this side and bring p1 here. p1 plus, q by p power 1 p1 plus q by p square p2 plus so on. Can someone identify a pattern here? So this is a geometric series, right? So
Yes, sir.
yeah, so you have a geometric series here, right? And then there is a standard formula for sum of geometric series, correct? Correct. At the same time, what is p100?
One.
Yeah, so p100 is equal to 1. If you substitute p100 is equal to 1, right, in this equation, then you can get what is the value of p1, right? And if you substitute the value of p1 here, right, you will end up with this relation. Okay. I hope it is I hope it is evident, or in case there are any questions, people can ask. This brings us to assignment problem number 3 to us. Write a code, write a Python code to simulate random walk for gambler's ruin. Okay. For sake of simplicity, you can keep n equal to 100 hard coded, but keep that as a parameter so that you can change it if required. Take probability is equal to begin with 1 by 5, 1 by 5, and change it to 1 by 3, 2 by 3. I mean, keep these as parameters so that you can change it, and verify if you get pi is equal to this. Okay. Is there any doubt with this assignment? Okay. I don't want you to plug in the numbers here again, just like I have made it clear earlier, right? I don't want you to say that probability of 10, okay, I'm not asking to write a code to do this, okay, is equal to minus q, or minus 1 by 2 times whatever, right? And then just insert the values, okay, and then give me that. That's not what I'm expecting. What I'm expecting is you to actually simulate, okay, and come up with a probability. Okay, so what is probability that given that you're at place 10. Okay, so how would you do it is you'll start a simulation, right? Start with wealth at I is equal to 10. Okay, and let the random walk run. Okay, and if at the end of the trial, if you win, you call that as event 1. If you lose, you call that as event 0, right? So you do hundreds and thousands of such trials. So if you do 1000 such trials, okay, count the number of wins. Okay, count your wins upon 1000. Okay, then run the simulation for 10,000 times. Okay, then count your wins upon 10,000 and check that this probability converges to this. Okay, so in our session we have derived an analytical way of doing it. In code, you're doing to use a brute force method to be able to solve the same problem. Okay, and the reason why I'm repeatedly asking you to do brute force method, non-analytical methods via Python codes is because not all equations, right? So for example, right, if you have background of engineering, right, I think you know pretty well that not all integrations, I mean not all functions can be integrated. Okay, at the same time, not all partial differential equations can be solved, not everything can be solved, but given that we live in a probability experiment, everything can be simulated. Okay, so for whatever you cannot find a solution using an analytical method, you should be able to find a solution using a brute force method. But the point being that we have some questions like this gambler's ruin and all of that, where we have both analytical solutions and simulated solutions. So we can cross check our solutions which we get from simulated versus the analytical, and that's why we can verify. But if the partial differential equation does not even have a solution, okay, you don't know whether you're right or wrong. Okay, so to do that, you need to have an understanding built as to what is happening at the back end. Okay, so I hope this is okay for everyone. Is there any question here? Is there any question with respect to understanding the assignment and whether or not you follow it, or what is the ask? I will. So there are many resources which discuss these things, right? So we have gambler's ruin problem, and this solution and all of this, right? So I will be sharing these PDFs with you so that you can go through these again and again. So these are much better written and all of that, right? So you will have some context to fall back on. Okay, but the idea is you should understand the things in the context, right? If you follow just a random material, right, the chances that it may not complete the same thing, the same rigorousness, okay, is high. Okay, so for example, the first random walk and the derivations which we have, right, we have covered it from these notes. Okay, where these notes talk about how to get at point X and 2k minus 1 and all, right, whatever we derived. Okay, this is exactly where they are. And then these probabilities going at point, taking k right steps, left steps, and all of that. Okay, so you will find materials, okay, for all of this, but understanding the rigorousness of all of this is important. My suggestion to you is, whenever you would read this material, for example, you look at this. Okay, all of it is given in terms of symbols, right? So you have L's, M, so directly they have started with a very generic step. Not everybody follows it, right? So you need to simplify. Okay, not every white paper you will get will be a simple version. Okay, sometimes if you have to do some quant research and if you want to read some white paper, okay, so you should, even if you get something like this which is direct a generic solution, you should start with simple steps first. Okay, you should put L equal to 1, okay, Q equal to 1 by 2, 1 by 2, and manually try to work it through one by one. Okay, directly they have come to this conclusion. Okay, but you should do it step by step. What all steps it can take, how can it go, where can it go, right? And then you should be able to reach to this yourself. Okay, and then you should be able to follow it. Okay, so I hope so. Like I said, right, you're seeing the build up. Okay, you're seeing the build up to a movie, right? So like before war, right, you need a lot of things, right? You need arrows, you need to learn arrows, swords, spear. So you're learning all these basics one by one, right? Yet we have not really touched upon something within quant finance yet. Okay, we are only looking at preliminaries and all of that which is required so that you can start learning quant finance. Okay, and you miss any one of this. For example, the first session we started with probability measure. You miss probability measure, then you miss why there are two probability measures. Then you miss how can you change from first probability measure to second probability measure. Then you miss everything going ahead, right? So it is important for you to stay connected with whatever curriculum you're learning. Okay, stay connected with it and make sure that you understand it. You can ask, you can stop me at any point in time. Okay, this concept doesn't make sense, this thing doesn't make sense, why are we doing this, why are we doing that? Okay, please do stop me. Okay, I am deliberately choosing simple, easy numerical examples so that first that concept can be driven into thought, and after that we go to generic symbols and generalize it and make it palatable. Okay, and of course the last step is, how do we know that we understood a concept, right? We know it only when we, oh, so this is Richard Feynman's technique, right? So what he said is, if only you can explain it, okay, well, to a 5-year-old and all, right, then you have understood it, otherwise you are not understood it. So the dumbest person you will find on the earth to explain is a PC, right? So if you can make it understand your thoughts of your understanding, only then you can say that you have really understood what you have learned. Okay, that's why I'm stressing on writing codes. Okay, of course, if you find, we'll have Wednesday sessions and all to discuss in case you're struggling to write the code. Okay, so there we can discuss what is the issue, how generalized to go, how specific to be, or how customized to be. We can discuss there. If the code is getting too complicated, then don't write it for an extremely general case. Okay, write it for a specific case, and just like we solved it for specific case, right? We solve it for n equal to 100, we solve equal to plus 1 minus 1, we solve it for 1 by 2, and then we build on it to make it generalized. Okay, similarly for your code, write it for a very specific case to begin with, and then parameterize it. Okay, then write functions, and then write loops, and then make it more general, and then write the efficient code. Okay, so that should be the steps which you should be following. Okay, any questions so far here? Can someone tell me how does this probability, okay, relate to how much initial wealth you have? Hello, am I audible?
Yes, sir.
So can someone tell me this, right? What is the probability, right? How it is associated with initial wealth? What is my likeliness of winning this game if I start with different initial wealths? If I start with low initial wealth, what is my probability of winning this game?
There is no relation.
Yes. So let us put, like we discussed, two extreme cases, right? If you have zero wealth, then you cannot win this game. If you have all the wealth, then you have already won this game, right? So I don't know exactly how this graph looks like. You can also plot this graph and check. So you start from these are your probabilities, right? And you start with this initial wealth, and then you're here, right? So maybe it looks something like this. So this conforms to the old, very old, I think there is a very old Hindi saying, right? पैसा पैसे को खींचता है. Okay. What roughly translates to is, wealth attracts wealth. Right? So if you are wealthy to begin with, the likeliness of you becoming even more wealthy is much higher in a fair game, which is driven by only probability and nothing else.
But it could also decrease with more aggressive strategy. I mean, it can also lead to ruin if the strategy or the model is going against.
No, I mean, what do you mean by model is going against?
I mean, we are starting with some initial wealth, and let's say we have all the money in the world, and then money attracts money. But what if the strategy goes wrong, leading to
What do you mean by strategy goes wrong?
I don't know. It could be anything, right? Strategy is not attracting more money.
But why will it not attract more money?
I don't
I mean,
know.
what you can do is simply calculate, right? If you have 90 rupees, right? What is your probability to go to what is your probability of winning the game? Okay. And if you have 60 rupees, what is your probability of winning the game? Correct.
Yeah.
Which will
So
be
we have to come to that optimal initial amount to start with.
What is optimal initial amount?
That's what I don't know.
No, there is no such thing as optimal initial amount. Point is, I'm telling it is already rigged against. Okay.
Right.
You can win this game only you have more than 100 rupees or 100 rupees. Right. I mean, the question is, if you are already at 100, why would you go to 100 again? Okay. So that's a redundant question. My point is, you would have already won it if you have already won it. That is, you already have 100. Or if you are at 90, okay, you are very likely to win it. Correct. If you are at 50, you are much less likely to win it. Okay. And if you are at 10, you are even less likely to win it. Right. So of course, all of these are also functions of Q's and P's. Correct. If you can tilt Q in your direction, then things start changing. Right. So you can, I don't know how again the graph looks like. Maybe you can plot it. But on one axis, you can have P increasing, and this is probability of winning, right? And here you have initial wealth I, correct? So with a certain initial wealth, okay, and let us say probability is 1 by 2. Okay, so your so you have the same probability of 1 by 2, right? So with initial wealth, maybe it looks like this. Okay, so this is a cross section of a plane, correct? So the graph which I plotted, right? So with increasing probability of winning, right, maybe your odds keep getting better. So if you have another plane, okay, at a different probability, right, your chances of winning go up drastically, right? And you become 100% much before, correct? Here you become, let us say, 99% at 99 rupees. Here you become 99% at 70 rupees. right? So your graph has a different slope and all of it, right? So if you plot it, you'll come to know this better, right? And with much lesser probability, you have even much lower chances, right? So it will something be like this, correct? So if you join this, then you will get the surface. Okay, and then you will come to know how it is affected by probability and initial wealth. Okay. So the house always wins. Okay. I don't know how if you have been to casinos and all. Casino starts with infinite wealth. Correct? Relative to you. Okay. So casino is already destined to win, even if it is playing a fair game with you. If it does not rig your dice, okay. You people must have seen roulette, right? People must have seen this roulette wheel, right? This has number one. Yeah, roulette. So you have 1 to 36 numbers, right? You can choose even numbers, odd numbers. They rig the game by keeping 0 0 and all of that. Okay, that's a different thing. But even if they don't rig the game, correct? If they put only numbers from 1 to 36, and so you can decide your probability of winning by choosing combinations, right? They allow you to bet on even numbers only, odd numbers only, red only, whatever, correct? So let us say you bet only on even numbers, right? Then your probability of win is 1 by 2, correct? And probability of loss is 1 by 2. Okay. Let us say you start betting with 1,000 rupees. Okay. So your probability of win to go to 10,000 rupees, okay, depends upon two things. One, what are the probability of winning and losing? And second, what is your initial wealth? The lower is your initial wealth, the lesser are the chances that you will make up to here. Correct? I think that is what we just established, right? So the casino attracts more number of people who are much less wealthy, right? Then casino will be winning almost all of those games almost surely again and again. Casino is likely to lose only when it enters into a bet with a guy who has as much money as much the casino has. Only then the game starts becoming fair. Okay. So person who is starting with 1 lakh rupees versus maybe 100 crore rupees and all of that, right? And casino itself has 100 crore. Then you're more likely to win. Okay. Versus you start with 500 rupees, okay, and then go on to win 100 crore rupees. Okay. You're much less likely to win, even if it is a fair game. Right? I hope.
So can we figure out, like, based on the target goal that we want to achieve with the amount we
Yes.
have?
Yes.
So what is the level that that we will go broke, and what is the level that we need to have to achieve the level we are targeting? Can we figure that out based on our situation?
Yes. So what you're saying essentially is if you start at no, so what you can figure out is, let us say you start at 1,000 rupees, right? And you're
Yeah.
always going to bet on even numbers. So that is the best probability that you can get, right? In casino, you can never get a probability of 0.67 or anything more than 0.5. If you must have seen the odds, correct? So you can only at the best get probability of this. What you can find is if I start with 1,000 rupees, right? And assume some number for casino, okay? Casino has, okay, 1 crore rupees or 10 crore rupees. You can find what is your probability of winning, okay? And probability that you will go broke. Okay. You can actually do this as a part of this assignment or exercise, and you can check if you win, how many times do you win? If you play the game 1,000 times, how many times do you win and all?
No, we need to know, like, I'm trying to ask you, like, when do we need to go home, and when do we need to continue playing?
So you will go home. I mean, So yes, so if you have a certain goal in your mind, right? So like I said, you can only calculate probability. Okay. For example, if you have 1,000 rupees in your pocket, okay, and your goal is to win 10,000 rupees, right? Yeah, what you can calculate is expected time, right? For example, expected time to reach from 1,000 to 10,000, right? Or you decide that I don't want to be fully broke, right? I will give up at 300 rupees, right? I keep losing money, okay? Per bet, I'm putting 10 rupees, okay? And I keep losing money. And if I go anything below 300, okay, I'll pack and go home, okay? That is up to for you to decide where will I go back, okay? And you have kept a goal of winning 10,000 rupees, right? So you say that as long as I keep winning until I lose so much that I end up with final wealth of 300, I'll go home. Correct? This is what you're asking.
Right,
So,
right, correct.
so there is a solution for that. Check where that is. Okay. So essentially what you do is, yes. So as you see here, right? You replace, so B is the amount where you're going broke, correct? And correspondingly for that n number of steps, whatever you'll have to take. And A plus B are your total number of steps, right? So your capital N gets replaced with A plus B. Okay. So if I'll share these notes with you. Okay. So let me give a numerical example of that. Okay. So Ellen bought share stock for $10. Okay. It is believed that stock price moves up by a simple random walk of 0.45. What is the probability that Ellen stock reaches high value of 15 before a low value of 5? This is similar to what you're asking, right? So before you go broke, what is the probability that you win the game before going broke? Okay, that is given by these probabilities, right? So just with respect to I and N, you replace with A plus B and B, right? And you get your probabilities. I'll share these notes with you. So coming back to our first session, first questions, right? I mean, I hope there are no questions in the portion that you have covered today. I hope there are no questions. Is this what we did today? Let me see. So I think there were two questions asked, right? One was, if you have a natural probability measure and you want to, win the game and all of that, right? So what is the relevance of bias in probability measure P, correct? And second is branching off of QF from ML of P versus Q. So relevance of bias in P, okay? So point is, you can, so let me explain this by virtue of linear regression, okay? So if you have a linear regression equation for a random variable y, okay, is equal to ax plus b, okay, and if I give you sample points, okay, so if I give you some sample points, and if I ask you to run a regression on this, right, then essentially the best you can get is y hat. Okay, you will never get y, correct? So you will get y hat is equal to ax plus b plus some error term, such that error term is equal to y minus y hat, correct? In the same sense, if even if you have all the information, all the data in the world, the best you can do to find natural probability measure, okay, is p star or p hat, right? And not really p, right? And this is where the variances and biases come in, correct? So I can say P minus P hat as your bias, okay? Or this is your error, correct? Now this error depends on your quality of model and all of that, how many variables you have incorporated, what is your parameter. So what is the confidence level of your parameter, statistical confidence and all of that, right? The more accurate the model, the lower will be the error and the closer you will be towards your real probability measure, right? Else not. Okay. So if the bias is high, then your errors will be higher, correct? You won't be predicting it more correctly. And in that case, you will be using certain model. Okay. So if your probability measure says, actual probability measure says, the probabilities of stock going up and down are 0.55 and 0.45. But if your p hat says, due to statistical errors, it says 0.45 and 0.55, correct? Then you're doomed for bust, right? Because the action which you need to take here, okay, are exactly opposite of action which you need to take here. Okay. So if you are very close to the probabilities where you need to flip your decision, okay, and your errors are large enough which flips your decision, okay, then bias has substantially larger significance. If instead, okay, if your natural probability measure says probability of stock going up is 0.9, down is 0.1, and if your model, predicted model, says that that probability is 0.85 and 0.15, so you are not likely to lose much. You will still lose money, but not much. Okay. So this is the relevance of bias in natural probability measure. And then branching off of QF from ML, right? P versus Q. So I would say that, field of quant finance is largely divided into two parts. So you will see a lot of hedge funds, a lot of investment firms, okay, they use ML models. Okay. So their objective is to, starting with an initial wealth, right? Their objective is to make money, right? And they make money by taking positions in underlying derivatives and all of that. Okay. So for them, it is important to know this, correct? Because the better estimate of P they will have by using some model, the closer they'll get to finding whether or not there is an opportunity in particular stock, underlying or whatever, correct? And if you see QF, right? So for example, if you have investment banks, okay, what they do is, let us say they sell exotic derivatives, okay, and they hedge it perfectly against vanilla derivatives, right? So this combination works for them if there is a perfect hedge between these two. Okay, in other words, if their portfolio is risk neutral, then you will ask, if their portfolio is risk neutral, where do they earn money from, right? So they earn money from commissions and all of that. Okay. So if I have sold you a derivative, okay, I'll sell a derivative which gives a payoff of, +1 to guy if something happens and -1 to guy if something does not happen. Okay. If heads, okay, and if tails. I'm giving you a simple example. We'll come to specific examples later. Okay. So this is what investment banks do. They sell one contract to a guy, okay, which pays +1 if, let me write it, keep the odds slightly different, okay, so that we can do some expectation now. So 1, okay, so so 1 for heads, okay, with probability, 1/2, and let us say -2, okay, for tails, okay, with probability 1/2, let us say +2, okay. So they'll ask this guy, okay, they have sold one exotic derivative to a guy which gives this payoff, okay. Now, what is the fair value that this guy has to pay for this contract, right? This guy, fair value this guy has to pay is, okay, 1 by 2, 1 into 1 by 2 plus 2 into 1 by 2, right? So this guy has to pay 3 by 2. Okay, so investment bank will instead of charging 1.5 rupees, they'll charge 1.501 rupees to this guy. Okay, and similarly they will sell the opposite bet to the opposite guy, right, where that guy has to pay this, okay, or pay this for heads, okay, and for tails. Okay, so payoff of this is minus 1.5, correct? So to this guy, instead of paying 1.5, investment bank will be paying 1.49 rupees, okay, to this guy. Now both these bets are hedged for investment bank, right? So there is a perfect hedge. To one guy, the investment bank, if this payoff comes, needs to pay 2 rupees. If this payoff need comes, pays 1 rupee. On an average, it pays 1.5 rupees, but it has collected this much amount. Okay, this it has hedged against this guy, to which the investment bank is paying this rupees with this probability, these rupees with this probability. Okay, and that is why it is paying 1.49 instead of 1.5. Okay, so the difference between these two, right? So 1.501 minus 1.49 is what an investment bank earns. But for this, it is important that this should be perfectly hedged. Okay, if this is not perfectly hedged, then there's a problem for investment bank. That is why here the objective function is completely different. Okay, so the underlying security could be mispriced or whatever, right? That investment bank does not care about. Okay, for example, whatever information is available in the market that is incorporated not in stock price and all, that is not what is a problem for investment bank. For them, the problem is the net position. Okay, the underlying and its derivative. Okay, if they can be perfectly hedged, then investment bank is okay. But for hedge funds, finding the actual probability measure is important, whether that problem, that whether the stock is supposed to go up or down and all. Okay, it is not relevant for them to be correct in risk neutral sense, but in actual sense, for these guys, the objective is to be correct in hedged sense, in perfectly hedged sense, and not really in absolute sense. Okay, so any questions? Shortly, I'll send out these assignments, these notes and everything. Okay, and tomorrow the things which we will target to cover are these. Okay, we'll target to cover Brownian motion even before. Okay, we'll require Brownian motion. So we'll require Brownian motion. Then we'll start with quadratic variation, right? And the need for quadratic variation. Then we'll see ordinary or partial differential equations. Okay, with an example. Okay, then we'll see Taylor series expansion for continuous differentiable functions, and then we'll see Ito's lemma. Okay, and Taylor series for Ito's, right? And why that is different from. So we are trying to build a base that the calculus which we have studied so far up to class 12th or engineering, that calculus is not sufficient to handle stochastic processes. And we are going to see a reason why that is not sufficient and what different kind of calculus we require for it, which is stochastic calculus. So we'll build a foundation for it. And tomorrow we would be having another 3 assignments on similar line, just like we had 3 today. So just a heads up for that. So any questions? So there is one small topic left, right? We need to formalize what is Markov process and what is martingale, okay, and give an example of each, and give an example of a process which is not Markov but a martingale but not a Markov, and all these combinations, so that we understand these better, and then we can move on to Brownian motion, then to quadratic variation, then to partial differential equations, and then to actual stochastic differential equations via Ito's lemma. So this will serve as our background for Black-Scholes derivation and all at a later stage. Okay. So any questions so far? In terms of materials, right? So I'll be sending out the materials today for whatever we have covered today, plus the actual original source material from where we have reference the study.
So when do we need to complete the assignment?
So I think it would be better if you at least attempt all 3 assignments before Wednesday. Okay. The idea is before Wednesday, ask all of your questions and doubts. And my expectation is by the next weekend, right? You have a working code, right? What we can do is we can. I was earlier thinking of pushing it to Git and all, but I think Git has restrictions to number of people who can push it and all. Okay, to the code to that. What we can do is we can consolidate. So write your scripts in Python. Okay, in a shared drive, each of you with your name, you can create a folder. Okay, and paste it as a PDF. Okay, so that
so this is the first assignment, right?
So we have total 3 questions for our first assignment.
This is the first assignment, yeah.
Yes, assignment 1, we have 3 questions.
Okay. I mean, in the last session, you did not give any. You did not give any assignment.
No assignment in last session because we did not have enough basics. So now we have basics. We have 3 questions of the first assignment, and then we'll have tomorrow another 3 questions for second assignment.
Sure. But writing Python code, you would suggest writing in Colab or Jupyter Notebook?
Whatever is comfortable to you.
Okay.
Whatever is comfortable to you. The only point is I would like to see your final script. Okay. Whatever is your final script. Okay. I will pick some random scripts. Okay. If you want, you can it can be anonymous, so you can just keep some identifier for yourself so that you know it's your script. If you don't want to disclose your name, you can pick a certain scripts. Okay, and I'll walk through the scripts. Okay.
So you want us to write a script on random walk?
No, I have given 3 assignments, right?
Right. Yeah. Actually, I did not write it down.
Yeah,
I'll take it from the group.
Yes, what I'll do is let me write it down explicitly. Okay, but let me walk you through again. Okay, it should not take long. First is this. Okay, first assignment is this, that okay, you have coin tosses, right? So there is a RadonNiko derivative, right, which says that expectation under Q, right, of X is equal to expectation under P, Q by P, and all of that, right? You have to verify this, okay, for a problem which I have specifically mentioned, right? So we go to the Jamboard. Yes, so this is the problem, right? So your omega is actually 1051. Their natural probabilities are 1 by 3, 1 by 3, 1 by 3, and you have a probability measure Q such that the probabilities take into the consideration of likeliness of payoff. Okay, the more the payoff, the less likely it is. Okay, so let me write it down. Okay, probability Q is as per likeliness of payoff. Likeliness of payoff, where your payoff is this, right? So the lesser the payoff, more likely it is. more the payoff, less likely it is, and so on and so forth. So first build one probability measure which takes that into account, and then write a Python code where you can verify these results. Okay. The second question for us is regarding random walk, right? So regarding random walk, the question is if you have a transition probability transition density functions, right? So this, right? So you need to verify a result for probability density function transitions. Okay, so how the transitions are happening, and given that you are at a certain state, what is the probability of reaching to a certain different state? And what is the relation between the transitions, right? So probability of reaching at point X at n plus 1th toss is given by probability, intermediate probabilities and the way to reach at X from Y. You're standing at Y at nth coin toss, then you have to reach X at n plus 1th. Okay, that is related by this probability. So this is this. Then the third question which we had for the day is about the gambler's ruin, right? So the gambler's ruin is, starting the experiment with a certain initial wealth. You have to reach to a target initial wealth with certain probability of win and loss. So if you start at, let us say 10 rupees, you have to reach at 100. Okay, you have to see whether or not you reach 100 in one of the trials. Okay, so you keep repeating this experiment again and again, and let us say do 1000 trials, 10,000 trials, or whatever. Okay, and for out of those 1000 trials, how many times did you win and how many times, okay, did you not win? So probability of win will be equal to number of times you won divided by total number of trials. This is the third question.
Okay.
So this is assignment number 3. Okay. So we are towards our end of session. Try to write the code as much as possible without any custom Python libraries. There are libraries for everything. You have a library to generate a random walk. You have a library to generate everything. Okay. So the code is about you doing it yourself. Okay. So you thinking it out, you doing it, and then you plotting. So let's see how this goes. Okay. So I'll share these assignment questions and the content which we have covered today. Let me do it right away. Okay. So let us do PDF. Let us do stochastic process and gambler's ruin. Okay, so where is this? This is the one, right? So let me this gambler's ruin.
So are you trading in the Indian market also?
I used to trade. I have stopped trading.
Now you are investing for long term.
Yes.
And in investing, long-term investing, all these concepts will be helpful apart from trading. Of course, trading in trading it's helpful.
Yes. So we'll discuss about investment quantitatively as per quantitative finance. There are 3 ways to invest. There is fundamental analysis, there is technical analysis, and there is quant. So we are going to look at investing via the lens of quant. Okay. So that will give us an idea of how a person who knows quant finance will look at investing. Okay. What strategies he can use, how a strategy is formulated, how do we think about it and all. So we'll discuss that most probably in the fourth week.
Sure.
Okay, so we can close this session for the day, right? In case there are any follow-up questions, we can continue on our group chat, and there we'll see how it goes from there.
Thank you.
Okay, yeah, thanks everyone for joining.
Thank you, sir.
Thanks. Yeah.
Thank you,
Bye.
sir.